there's this thing about atoms. When they make bonds, remember those lines mean bonds, right? I know a lot of you are not taking conceptual physics, so please make sure you're paying attention. Those people that are taking conceptual physics might know this already. Let's look at water, because water is the prime example. When they make bonds, some elements are I'm going to use the word stronger. I'm going to use the word stronger than other elements. Some elements are stronger. And we call that strength electronegativity. I'll let you figure that out. Electronegativity. What that means is, it's a horrible arrow, you're right. I made fun of you, but actually I'm the one that should be made fun of. I apologize. Is that better?
Yes.
Okay. So the sometimes you kids kill me. All right, so anyways, electronegativity, it just means that it's strong. I'm going to say this word stronger. It means it pulls on the electrons more. All right, and it pulls on the electrons more. Now, in the case of hydrogen and oxygen, hydrogen's still pulling on the electrons. What happens if one side's pulling more? You ever see tug of war? So if you see a game of tug of war, there's a rope. There's one person or a group of people on one side. There's another group of people on the other side. And there's a flag in the center, right? And that flag is sitting there. And there's a mark, usually a stake of some kind, that marks the midpoint. And if they're equally strong, then the flag stays in the middle, right? But when one group starts to win, what happens is that flag gets moved over. And if we were playing tug of war, it'd be on my side. So the flag gets moved over. I'm just kidding. And so the flag gets moved over here, all right? Moved over to this side. This guy's stronger. Now, are they still connected?
Yes.
They're still connected. It's just that this guy has the flag on his side more often, right? And maybe this side the flag gets pulled over here once in a while, but it gets pulled back here because this group is stronger. Do you agree? Do you see that?
Yes.
Well, that's what's happening with these electrons. What's happening with these electrons is they stay more often around the oxygen. And so what happens is the oxygen becomes slightly negative, not fully negative because they didn't take the flag, they didn't take the electron. It's just slightly negative. The other side gets slightly positive and slightly negative. So what happens is that you get something called a polar bond. A polar bond. This polar bond, what happens is that now when you have well, let's first talk about what polar is. Who knows? Give me some words that go along with polar that you've experienced. Please try, although I like the Polar Express, it's a great story. It does have, I guess you could use the Polar Express if you want. Go ahead. Yeah.
Polar bear. Wait, what?
Help me. Help me out. All right, so polar bear is a word that you've heard. Why do we call them polar bears?
Because they live in the south.
Not because they're in the cold, although it is cold where they're from. Why do we call them polar bears? In North Pole. But they live in the poles. Yeah, they live by a pole. What is a pole? So let's look at what a pole is. On the Earth is spinning on an axis. By the way, it's not a perfect sphere. The Earth is more of an ellipse than it is a sphere. But because it's spinning, it bulges out in different places. In any case, the Earth is spinning, right? Towards what? Towards which side? Well, tell me. East or west? East. How do you know it's east? Because the sun's rising. So if you're looking at the sun, Yes, this is a sun. Deal with it. So if you're looking at the sun, as you spin towards it, you see the sun rise. All right? So it's spinning. So there's two sides, right? Anytime you have two sides, of course, in this case, we call this side north, and this side we call it south. That's just what we called it. We could have called it shoe and sock. It wouldn't have mattered. You know, it's north and south is what we called it a long time ago, and it's stuck. Yeah.
Don't the poles move?
It's a good point. Every 10,000 years they flip. And there is a little bit of movement one way or the other. In fact, we're worried that there's going to be a polar flip soon. And some people think that when the poles flip, the electromagnetic field that protects us against cosmic rays goes away. And if that happens, then we will be microwaved like your hot dog in your microwave oven. So it's not a good thing, right? But other people think not. It's a big, long conversation. I don't want to get into it. But yes, they will flip or they do move. But for the sake of north and south, and we will talk about this when we talk about continental plates shifting. But in any case, pay attention, please. So the Earth is spinning towards the east, right? And away from the west. So, but the key is what? That we have a north and a south, two opposite sides. That's why we call north and south. That's why we call them poles. All right, any other pole words that you know? Yeah. A polar molecule, that's what we're looking at here, polar molecule. This is a polar molecule. But I guess I'm trying to get at to why do we call it a polar molecule, what makes it special. Yeah, but let's think about any other words we know of as polar first, yeah. Magnetic poles, that's the one I was hoping someone would say. So oh, did you? I didn't hear it. I'm sorry, I didn't hear it. I see you sneaking food. I'm hoping that you're going to not leave a mess, and secondly, you stop. Secondly, stop. Don't eat. So anybody that's played with magnets knows there's a north and a south side of a magnet, right? Again, what does north and south mean? That means that they're opposite sides. Which means that if you remember what we said about opposites? They attract. So if we take this, we know they're going to attract. Pay attention, please. And if we did this here, we know these are going to do what? They're going to repel, right? So these are going to push away, and these are going to pull towards each other, right? To use the same notation that Miss Simpson uses with you. So what happens is that these will attract, these will repel. These are opposites. This is what we call polar, right? So magnets are actually a really good example of what's going on with these water molecules and with polar molecules in general. Because now you have two sides, don't you? You have a negative side and a positive side. Do you agree with that? Yes, go ahead.
Oh, I was going to say dipole.
You've heard of dipole? It was in the packet? Good. But did you understand it? All right, so dipole just means you have two poles. So very much polar. We call it dipole forces. There's three weak types of bonds, and we already talked about one, hydrogen bonding. We talked about another called disulfide bridging, right? Yes? Disulfide bridges are formed when? Yes, we did. Yeah, we did. You didn't watch the video? Did we talk about hair? Yeah. We did talk about hair. And you better look at your notes again. You better review again. And what happens between two cysteine amino acids? Yeah. They attract because of what? They form a what? Disulfide bridge. We'll do it in a minute. I'm going to spell them all out for you in just a second. So all these are polar bonds. So what happens is that when you have certain molecules, and they, like water, they align in this way. I'm going to answer this phone and then let you think about why they align like this. Look at how they're aligned. Room 374, Mr. Mendoza speaking. May I help you? Sure. Yes. Does she need all her things? All right. Bye-bye. Tia, please go to the office. You'll need all your things with you. Huh? Yeah, I'm gonna keep going, and so I'll post this at the end of the day, okay? So make sure you look at it. All of you, wherever we stop, my guess is that the next class will get a little further throughout the day. So please make sure that you watch whatever you haven't seen on this video this evening so that you're ready for the exam on Friday. Yeah?
I was gonna answer the question.
All right, go ahead. Why are they aligned like this? Why do you see these things aligning in this way?
I think it's because like the oxygens, they're repelling each other, and like the oxygen and the hydrogen are attracting.
That's right. So what happens is that because, remember what we just said, this side is partially negative, this side is partially positive, partially positive. Notice I'm drawing this delta. It's lowercase delta. It's a Greek letter. It's not an S. It looks like an S, but it's not. This is partial negative. That's partial positive. So that what happens between the positives and the negatives, of course, oh, I'm sorry, I missed one. What happens is this force, this pull between the positives and negatives happen. There's an actual pull, and it forces the molecules to align in a specific geometry. The geometry is very specific in water, and all polar molecules. They form this lattice. Hold on a sec. But so we call this type of attraction. Notice that did I say anything about sharing electrons? No, I did not, because they are not sharing electron between molecules. That is not happening. The only sharing of electrons between the hydrogen and the oxygen here. Is that clear? Where you see lines, you have sharing of electron. This is an intermolecular force. Just like interstate means what? In between states. Intermolecular means what? In between molecules. So this is a type of intermolecular force that's called hydrogen bonding. Hydrogen bonding is probably one of the most ubiquitous things that are happening in biology. Almost everything that happens in living systems has a lot to do with hydrogen bonding. DNA folding, RNA folding, water being attracted to water. The boiling point of water is because of hydrogen bonding. Ice floating in liquid water, solid water floating in liquid water, is because of hydrogen bonding. Water going up the tree, from the tree roots up into the leaves, hundreds of feet. In some cases, in the case of a redwood tree, maybe 1,000 feet up. I don't know if that's how tall they get, but if it is, that's how far it goes. That water goes up there. They don't have little hearts pumping. No, they don't. Hydrogen bonding moves it up. One of the most important forces is actually a very weak force. Very weak force. And I wish I had time to go into it in more depth. It's so important, but we just don't have the time. Another kind of intermolecular force is when you have one cysteine amino acid and another cysteine amino acid. They have a sulfur here, and the sulfur has this polar type of bond, and they form this bond between themselves called a disulfide bridge, which goes to what we've already talked about with hair folding and proteins folding, that every time you have a lot of cysteines, those proteins end up folding a lot more than proteins that don't have cysteines, because they can form these disulfide bridges. But also, hydrogen bonding is involved in folding of proteins as well. So you need to consider that it's not always disulfide bridges in proteins, but certainly it's intermolecular forces. So hydrogen bonding, disulfide bridges, there's things called dipole-dipole moments. So the difference between dipole, and hydrogen bonding is pretty consistent. Dipole, and something else called London dispersion forces. Those two types of forces, they change. So you can have a dipole or London dispersion force for a second, and then it switches off and then switches back on. So it's kind of like a flickering light, right? Where these two are more like a light that's standard on, or if it's not there, then they're not there. But if this is present, it's going to stay present. Are we clear? All right.
Can you re-explain that?
So all of this is because of uneven sharing, right? Because of electronegativity differences between atoms. In the case of hydrogen bonding, it's specifically 3 elements. It's generally hydrogen. Whenever hydrogen is bound to oxygen or nitrogen, but usually it's just oxygen, but, all right? The electronegativity differences are so large that the electrons end up being around one atom more often than the other. And hydrogen tends to be the more positive one, and the other one tends to be the more negative one, and that causes these little, can we just call them, these molecules end up acting like magnets. And they end up pushing and pulling each other in such an arrangement as to form some kind of geometry. Is that clear to everybody? All right. So that's water, that's polar bonds. And that's really important. These kinds of intermolecular forces are very important. Now that brings us to something that there are consequences to everything. I hope I've tried to teach you that there are consequences to everything. I hope that you learn that, because it's an important lesson, but just know it is a nonpolar solvent, though, but it's an important lesson for biology. So if you have this molecule that has just a little bit of a charge over here, maybe it has this carbon with this kind of, maybe it has something like this on it. I'll just leave it off. But then you have all this big, long carbon chain. Something like gasoline or oil. Oh, that's too many bonds. Somebody should call me out on that right away. Nobody likes you. Okay. All right, I'm just kidding. Stop messing with me, man. Stop picking on me.
Nobody likes me.
All right, so you have all these. You have all these molecules, all these fats. These are lipids, right? If you've done your homework, we know these are lipids, right?
Yes.
So these are long, and then you have this stuff that we call water. We know it's polar, right? Partially positive and partially negative. Now this stuff that we call water, does this water mix well with fat? Does water mix well with fat? Anybody know? Does anybody know this?
No, it doesn't.
Why not?
Because opposite oil.
Okay, but
Too many bonds. Opposite the check.
well, here's what happens. The polar molecules then, they dissolve the polar molecules. And what that means, dissolving, do you see what's happening here with these waters? You see how they're mixing well? That's what dissolving means, by the way. Dissolving means mixing well. Polar molecules dissolve well in polar molecules, and nonpolar ones dissolve well in nonpolar ones. So it turns out that all of these, right, are nonpolar. Why are they nonpolar? Can anybody look at these and tell me why is this nonpolar? I'll give you a second. Think about it. You know what polar is. What's nonpolar? Why are these nonpolar? That's right, there's no opposites. It does have a slightly negative end, but what the rest of this is what? There's no charge. It's not an opposite, is it? Where all of these over here, all this in water, what is all this water? What is it? What do we know it has? Has a bunch of opposite sides, doesn't it?
Yeah.
So this side here, let me shrink this down. Oh. So this stuff here, this side here, we're going to go ahead and call, this is the polar end, the polar molecules, right? Another word, and this side over here is going to be nonpolar. So there's a saying that if you memorize it, you'll get it right almost every time. It's like, dissolves, that's right, like. So if you have a nonpolar substance, like, let me give you a list of nonpolar substances. Oil, very good. Another one is alcohol. Stop. Although alcohol is slightly polar, so it's another complicated. What is a complicated one? Oil, alcohol. Give me another one. I'll give you a permanent marker. Hand sanitizer is alcohol. So, and alcohol is actually an exception. It acts really funny, and there's reasons for it. I'm not going to discuss. It is a nonpolar solvent. Sorry about that. So, oil, alcohol, permanent marker. Another one. Shush. Try to focus, please. Nail polish remover. Which you also known as, is also known as acetone. Very good. Of course, kerosene, gasoline. These are all nonpolar. So this explains why this stuff, permanent marker, when you mark on your notebook with permanent marker and it rains, the water doesn't dissolve it. But if you mark with an expo marker and it rains, what happens to your stuff? It runs. If you use a regular marker and you mark on your notebook with a regular marker and it rains, your marker will run off, right? It'll turn into a rainbow. But permanent marker doesn't do that. I don't like the word permanent because it's not permanent. What could you do to get rid of this permanent marker? How could you make that permanent marker? Hand sanitizer works because hand sanitizer has alcohol in it, right? Let's use something else that you guys, a lot of you use, male and female nowadays. When I was a kid, so generally females. Nail polish. You put nail polish on your nails, right? It doesn't, you take a shower, and it doesn't run away, does it? Does it run? No, it doesn't run. But then all of a sudden, you use nail polish remover, which is acetone. What happens to it? It goes away, it runs off. Now, it doesn't run easily, but you have to scrub it a little bit, but it will go off, right? That's because these are non-polar solvents, not like dissolves like. So be clear on this idea that like dissolves like. Also, this explains why oil and water don't mix. Water is polar and oil is non-polar. They don't mix.
So just like when you dump oil into the sea, whatever, it just floats.
It floats, and you'll see a rainbows on the surface of the water because the light refracts inside is refracted by the oil and split into separate colors. So oil floats on water because it's less dense and it doesn't mix very well at all. Are we clear on this? I still got a couple minutes, so I want to emphasize this idea. There is another kind of lipid. This is a weird one, and this is called the phospholipid. And a phospholipid, you're missing a really big idea, and I'm sorry for you, but I'm going to keep going. A phospholipid is generally connected to two tails. It has two carbon tails. Some of the tails are bent because there's a double bond. Most of them only have a single bond. And this is what we call a phospholipid. It sits in, and what's interesting about a phospholipid is a phospholipid has a really highly charged area. That this end of the molecule is polar, and this end of the molecule is nonpolar.
Wow. That's weird.
That is weird, and there are consequences to that. This is what allows you to have a cell membrane. This is the cell membrane. The phospholipid will form the cell membrane. So next week when we talk about the cell, this molecule it's called the phospholipid. Lipid means fat. Is the basis of a cell membrane, with one side being polar, the other side nonpolar. If you were to put this together, what do you think the polar end is going to point to? If you put it in water,
Itself.
the polar end could point to themselves, or they could, if you put them in water, the polar end is probably going to point to the water. The polar end will be dissolved by water, right? Because water is polar, and light dissolves light. All right, we'll continue this tomorrow, or whenever we meet again. Remember, tomorrow we're not meeting, you have SATs tomorrow. You have SATs. We'll talk about it during, what do I call it? Advisory, yeah?
So there's not.
Polar have opposites, that's right.
So I have a question.
Yeah.
Does non-polar dissolve each other?
Yes, nonpolar, like dissolves like. So nonpolar dissolves nonpolar, and polar dissolves polar. Remember the nail polish and acetone? Both of those are nonpolar. Right?
Excuse me?
Nail polish and acetone, nail polish remover. I remember that example I just used. So that's nonpolar dissolving nonpolar. Permanent marker being dissolved by alcohol. That's what? An example of what? Nonpolar dissolving nonpolar. Okay? Remember that. And really, it's not this shouldn't be a positive here, it should be a negative. But when we're looking at this, what you have, it's real simple actually. The structure of it's very simple. It can be complicated to remember. You don't have to remember the structure. It might be clear, but I think it's important that you see it, especially this glycerol. Glycerol is just this 3-carbon molecule. It's just 3 carbons. It's an alcohol. No big deal. Off of one side, you have these long chains of carbons. It's just a long chain of carbons over and over. The first carbon actually has an oxygen on it, but the rest, do lipids have a lot of oxygen? No, they don't. They have some oxygen, but not a lot, all right? In fact, why don't I just start this on the next page here. So lipids have some oxygen, but not a lot. And what you have is this glycerol molecule, which is 3 carbons. And off of 1 carbon, you have this oxygen. The rest, you have 2 hydrogens. I'm not going to put the H's. I'm just going to draw this kind of a dash, if that's okay. That represents an H at the end of that. And there's an oxygen off this one. And then you have these 2 hydrogens again. Again, I'm not going to draw the H's. And in this case, to these 2 oxygen are attached these carbons, and one of the carbons has this. There's that carboxyl end that I drew earlier. Do you see that? You have a C, O, double bond O. There's that carboxyl end that we drew a little while ago. You see that a lot in biology, these carboxyl. They're very reactive. They're very good for constructing molecules, to building them together. So that's why you see a lot of them. So the carboxyl, remember, is C double bond O OH. That's that acid. That's right, that carboxylic acid business. Do you have to remember that? No, I'm not going to point to this and say, is this the carboxyl group? Is this the methyl group? I'm not going to do that to you, all right? I'm just trying to introduce you to the ideas. So just go along and try to remember it. If you do, great. If you don't, no sweat. But the big molecule, the phospholipid, you've got to be able to identify. So there it is. It just makes a big long chain of carbons. And I'm just going to have to shrink this up a bunch for a little bit here. Now these are all what? Carbon and what? Hydrogen. Remember these molecules don't have a lot of oxygen. These molecules are carbon chains, usually just carbon and hydrogen. So don't be surprised if you see that these things, if you see that these molecules are if they have very little hydrogen and oxygen, oxygen. Okay? So there should be no surprise there. So that's the backbone of a phospholipid. It's these things here, you see these two things, these two chains, they're called fatty acids. Why do we call them acids?
They have that double bond oxygen.
That's right. You have the acid. That's the acid part. Very good. Excellent. I love it when people think. The fat part is the long chain of carbons and hydrogens. The acid part is that tip, the C double bond O. Well, remember you still got that glycerol. You still got one left. You still have a carbon left. Well, it turns out that that carbon's attached to this phosphate group. And that's where you get what for this lipid? What do we call it? What part of the name is influenced by the phospho part, right? That's why we call this a phospholipid. Because there's two long tails of fatty acids, and you have that one phosphate. That's what makes it phospho. All right. Now that's attached. Again, this is a little extra, but as you guys say, this is doing extra. Attached to nitrogen, that's attached to a methyl group, RSSH2-3, and there's another CH2 plus. But it's irrelevant. That's not really the key here. The key is what? That you have a phosphate group, and the phosphate group is what? What's the phosphate group? It's polar. This part here, this head is polar. In other words, it has what? It has what? Two sides, a positive and negative. Polar means two sides, right? So it has a positive and negative. And because it has a positive and negative, it's polar. This is what we call this side. I'm going to go ahead and highlight this. This side's called a phosphate head. So this is a head. I'm going to go ahead and make it round. Yeah, in a second. That's a phosphate head. And then these things here are the lipid tails. Do you see that? So when we draw this, when you see it drawn, you're going to see it drawn like this. Oh, there's a pen. A head that we call this is another word. You should know it by now. I'll tell you in a minute. Hydrophilic head. And then you have, and they usually draw one that looks like this. The tail looks like this. I'll explain what this is in a second. A hydrophobic tail. All right, it's time to go. So go ahead and pack your stuff up and go. I'll finish this in the video. You can watch it, all right? If you're going to be absent for the exam, I don't know what to say. Deal with me, talk to me. Other than that, the exam is on Friday. It's a good question. The question is, why is this bent, right? And we're going to talk about it just actually, that's very important, the fact that this is bent. It has a lot to do with a lot of different issues, and we'll talk about it in just a second. Yeah,
So what is a polar molecule?
a polar molecule means the molecule has a positive side and a negative side.
So that was a polar molecule, right?
Very good question. This is not a polar molecule because the molecule is very long. It turns out very big molecules like a phospholipid can have a polar side. You see how this is positive and negative, and a non-polar side.
So if we got both looks, it's called
We'll talk about it in a second. But this is a polar head, polar head, and non-polar tail. You'll see in a minute. I'm about to talk about it. We're going to see it. We're going to construct a basic micelle, and we'll see. Okay? So, hydrophilic. The word philic means love. Philic means love. What does hydro mean? So what does this head want to do? Water loving. Right? It's a water loving head. Why do we call it that? Why do we call this head water loving? Because it's what? It's polar. It dissolves in water. No problem. Because it's positive and negative. Fair? This tail is phobic. This tail is hydro. What does phobic mean? Hater or afraid of. It doesn't like water. It moves away from water.
So what is claustrophobic?
It means they're afraid of small spaces. Anything phobic, anything the word with that end part here, phobic, means afraid of. In this case, afraid of water. You'll see why it's called that in just a minute. That's right. That's what that means. Excellent. So hydrophobic means non-polar. Hydrophilic means what?
Polar.
Polar. So it really is the bottom line there. Now, when you're dealing with a fatty acid, you're dealing with this long chain of carbons. It turns out that some carbons have a double bond to another carbon. So this has 3, has 1 hydrogen, not 2. The rest of these have 2 hydrogens. You see that? And that double bond to carbon, what it does is it bends the tail, bends it.
That's why I was like that.
That's why this thing looks like this. When it's bent, it's said that this fatty acid is unsaturated. You've heard of this before, right? Unsaturated fatty acids from your food. You can watch it on the labels. 100% unsaturated fatty acids. You know, all that in the commercial. Well, unsaturated fat.
Fatty acids.
So what you get is this thing, what this does is, what does the word saturate mean? First of all, let me ask you that question. Unsaturated. What is saturated? Something saturated. What does it mean?
Pure.
No. Salt? Well, I'll tell you. The word saturated means full. All right, full. Just as you can look it up and exactly what it means and all the root words, but if you see saturated, it means full. It means you're full. If you're satiated, you are full, right? If you have, so now, how many bonds can carbon have?
4.
4. So this carbon has 1, 2, 3, 4. So it is what?
Saturated.
Saturated. Now a saturated fatty acid looks more like this. All of the bonds have a hydrogen or a carbon on it. They have 4 individual bonds, except for the head, of course. So when you have a saturated fatty acid, it's a straight chain. When you have an unsaturated fatty acid, there's a bend to it. There's a slight bend to it. And there's implications there. There are consequences to that. And if you have if you have more than one unsaturated fatty acid, unsaturated carbon, then you have a what?
Oversaturated? I don't know.
A good question. This is called, a good guess, this thing is called a saturated fatty acid, all right? That's a saturated fatty acid. So this one here, I'm going to go ahead and put it in red. This is saturated, oh, I'm sorry, excuse me. Unsaturated fatty acid. You have to be able to tell the difference between these. So that's why I'm spending this time on it. All right? This one over here is called a saturated fatty acid. So this one has what? On each carbon has a what? Has 4 bonds. Except for the head. We're going to make that an exception. So here's this molecule. There's one that doesn't have it. So this is called a what? Unsaturated fatty, because there's one double bond in it. If you have a molecule now think about it. If you have a molecule, fatty acid, that has more than one double bond, you have this molecule here that has more than one double bond, right? The other one had 2 double bonds, right? 1 double bond. This one has 2 double bonds. What do you call this one?
What? I thought it had 3.
If this is unsaturated fatty acid because it has 1 double bond. Do you see it?
It got 2.
This is all single. We're not going to talk about the head. The head's an example, is an exception, right? Are we good with that? All right. No, that's all right. The heads are. It's a good point. You're right. There's more than one carbon with double bonds, but this doesn't count. We're going to call that the acid part, right? This is the acid part. That's part of the carboxylic acid. The fat part here, all the carbons have 4 bonds, right? So this is saturated. Unsaturated means that the carbons in the fat have at least 1 double bond. So this is unsaturated. What do you call this one that has 2 unsaturated bonds? Double. That's a good guess. Well, it turns out we call it poly.
Oh, yeah.
And you'll see it if you look at the labels, you'll see that olive oil, for instance, is a polyunsaturated oil. And you'll see that you'll see that various vegetables are polyunsaturated, but you'll see that animal fat is saturated for the most part. Well, that's at atomic level. Now here's what happens at the molecular level. What happens with saturated fatty acids is saturated, they line up like this. They end up laying on top of one another like this. They dissolve each other. They dissolve each other very well, and there's not a lot of room between them. So what they have is they have a higher melting point. They stick together well. Now, if this is in your bloodstream, that's not a good thing, right?
No.
You don't want these things sticking together really well, because what do they form?
A blood clot.
A clot, but not a blood clot. They form a clot called arterial sclerosis. They'll change into this like plaque. If this is your blood vessel, what happens is that it starts to form this mass in your blood vessel, in your artery or your vein, and it'll reduce how much blood flows through there.
And I can stop your bleeding.
And what happens is when you do get a blood clot, a big old blood clot, what happens to your blood?
Stop.
It stops, and you have what's called a heart attack or an embolism, and your tissues die. So having a lot of saturated fats in your bloodstream is not a good idea. There's still a bunch of arguments. It's pretty clear thus far that eating high saturated fat diets are not good. What's good about saturated fats is they have a high melting point. So if you want to cook, what are you going to probably want to use?
Saturated.
Because they hold together much better. So you see that a lot of restaurants will use oils that have a lot of saturated fat. In fact, most people that are chefs, they'll even use lard, which is animal fat, to cook with.
Water is animal fat?
Lard,
Oh.
Lard. That's an old school cooking. In fact, you go to the South, they'll still use lard to cook biscuits and make gravy. That's what they use. Biscuits and gravy, they're gonna use lard. It tastes delicious. I've had it.
The actual fat or like?
I mean, nobody scoops up a spoonful of fat, but when you cook with lard, it gives a taste to the food that you wouldn't get with like olive oil.
Alright, so I got a question. Alright, so
Yeah.
say like somebody don't cook with salt, right? But they like cook with lard, would it kind of give it that same flavor?
No, the lard, the saturated fat has a much different flavor, and it holds up really well when you're at high temperatures frying. Stuff that's fried, it works better. So unsaturated, things like olive oil, and actually olive oil I believe is polyunsaturated, you'll have to look that up, but I'm pretty sure that. So unsaturated and polyunsaturated being the best, these oils are really good for you. It turns out that they're really good for you because they tend not to do this. They tend not to form into these sclerotic blockages in your veins and arteries. All right. So it turns out that these unsaturated fatty acids and polyunsaturated fatty acids, the best is the polyunsaturated, right? But the saturated ones are just not good for you. Of course, there's the whole trans fatty acid business. It's even worse.
So unsaturated and nonpolar are like related to each other or something?
Well, unsaturated means just simply that the fat part, the nonpolar part, has a double bond. That's it. And what it does is it when you have one molecule next to the other, what does it do? What do they do to each other? They push away. So there's literally more room between the molecules, so they end up being liquid at room temperature. Have you ever cooked with butter?
Yeah.
And what happens in the pan after the butter cools down? What happens in the pan? What does it turn into? Well, hopefully, if you burn it, it's something different. But if you don't burn it, and you just cook it, you ever see what happens in the pan?
Oh, it'll get slippery.
It gets goopy. It turns back into butter again. Because at room temperature, butter's a solid. Why? Because it's layered up on top of itself. Because it's saturated. Butter is made of saturated fat. Saturated fat is a solid at room temperature. Unsaturated fat is a liquid at room temperature. You ever see olive oil? Is olive oil a giant block of olive oil? No, it's a liquid. Corn oil is what? Corn oil. A liquid, right? Liquids are unsaturated fatty acids if they're room temperature. If fats are room temperature and they're liquid, they're going to be these unsaturated, the double bonds. Now, why is that important? Because when you make cells, you also start to deal with this double bond and single bond stuff. So it becomes important in cells. Let's talk about that next. Any questions thus far before we go on?
Nope.
No? All right. So now let's put the two things together, water and fats. So if you have this water molecule, oxygen with two hydrogens, and you know that this thing's partially negative, and this thing's partially negative, and this one's partially positive, and this one's partially positive. These things are sitting there in water. It's called water. We know that, right?
H2O, yeah.
All
Oh,
right.
how you do that?
So we got these water molecules. The negative is going to point to the positive, right? Anywhere you see a negative, there's going to be the positive is going to point to it, right? So they're going to dissolve each other. They're going to line up. They're going to form a certain geometry, aren't they?
Yeah.
And they're going to form this geometry, and that's water. Now, if you have this water, and then you get this chain of fatty acids, a C, double bond O, single bond O, or actually you should put it the other way, just because that's how the people like to draw it. And then carbon, 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 carbon. Let's forget about the polyunsaturated and saturated for a minute. Let's just say it's a long chain of carbons, if you don't mind.
How many carbons does it have to have?
That's a good question. It can have a lot. The number each number is going to change what fatty acid you have. So linoleic acid has a certain number of carbons. The fat in and olive oil has another one, the fat in corn oil has another number of carbons. So it's a really good question. That number of fats, the number of carbons in the fat, that is determined by the kind of fat it is. So you have these fats. Now these fats, oh come on. What are they going to do in water? That's really the question. Especially if you have, so what are they going to do in water is they're going to float on the surface, right?
Yeah,
They're going to stay away, just like we did before.
like oil, right?
Like oil. But now, what happens though when we take these and add it to phosphate? And phosphate's going to be when we add it to phosphate, we're going to add it to a glycerol molecule, right? Phosphate's going to be added to this glycerol molecule that's going to be attached to these fatty acids. Remember that? If you don't remember it, you can go back and review it. So fats will just float on water, but these phospholipids are going to do something strange. Well, it's not really strange. You know what? I'm going to go ahead and draw it simpler. Do you mind if I draw it simpler? I think it'll be easier for you if I draw it simpler. What if I draw this head, right? That's the phosphate part, right? There'll be a phosphorus with oxygen. And there'll be other atoms in there, right? It's a bigger molecule than what I'm drawing, but there's a head. And that's that hydrophilic, right? Very good. The water-loving. And then I draw this thing. I'm going to go ahead and draw this straight chain, fatty acid. And I'm going to go ahead and put a kink in this one, right? There's that double bond is in that fatty acid. And what if we have a bunch of these?
They're gonna be what's it called?
If we have a bunch of these, what is it? What are these? Which ones? There's water. Here's water. Right? This is water. What's it going to do with these? Are they going to separate like regular fat? What?
No.
No. Something else is going to happen. What's different between this phospholipid and this just the fatty acids? They're not. Fatty acids are all nonpolar. Like does not dissolve. Like dissolves like. If they're different, they're not going to dissolve each other, so they're going to stay separate. What do you know about this molecule?
Oh.
It has two parts. It has a what part? Hydrophilic or water-loving part. What's the water-loving part going to do?
Oh, it's gonna combine.
It's gonna be dissolved by the water. It's gonna point towards the water. The part that doesn't like water is gonna point away from it. So that'll be this beginning of the lipid layer, the phospholipid bilayer. We'll talk about this. Next week. All right, and that's all the stuff that's going to be on the test. Everything that was on the other videos and this. Good luck.
What else was I say?
Let me record this. What happens over time is that the polar ends face the water, and the non-polar ends, they dissolve each other, right? Because like dissolves like. Do you see them dissolving each other? They're mixing. Remember, dissolving means mixing. Do you see it? Do you see what's happening? And they're going to form this thing. What do you call this? What's this? What's it forming?
A fatty acid.
Go ahead. What's it forming?
Fatty acid.
A sphere, right? It's a sphere. And this sphere is what's it going to look like? What's the sphere going to look like? It's going to be surrounded by water. That's negative, so water's going to surround it, right? So it's going to be dissolved. That's what dissolving means, right? What does that look like to you?
Looks like
Say it. Somebody said it.
a sun.
A sun? A star?
Nucleus.
Okay, like a nucleus, I guess. You can say nucleus. Well, so you would have like this sphere of lipids, right? On the inside would be all the fats, and on the outside would be all the phosphate heads, right? All the hydrophilic heads. And then it would be surrounded by water all the way around.
Like a lava lamp.
Okay, it could be a lava lamp. Well,
Looks like an island.
okay, an island. Well, it's what we call, in this case, because there's nothing inside, it's not alive, we call it a micelle. A micelle. And it's not M-I, it's M-Y. Hold on a second, I gotta do something here.
What is that? So that's making so many steps.
If you, listen, I can't keep going back. So, it's not M-Y. I always do that, I always want to spell myself. I asked you to turn off, I asked you to put them away, and you continue. Micelle. A micelle is just a sphere. It looks like this in 3 dimensions, right? Remembering that the outside's all covered up. The inside's with these hydrophilic heads. And the inside has these hydrophobic tails. So this is called the micelle. And micelle is just a sphere of, it's basically a fat ball. It's a ball of fat with the phospholipids though, where the lipids all dissolve each other, but it floats around in water. Why doesn't it float on top of the water? Why is it mixed in the water? Because the outside is hydrophilic. So because of that, it can float around. And guess what? That's detergent. That's how detergent works. That's how phosphate-based detergents work this way. So Dawn liquid, your detergent, your clothes washing soap, you put these soaps that look like this. There's a droplet of oil on your shirt. Here's this oil sitting there on the shirt. Let me draw it green so you can see it's the same. Here's this drop of oil on your shirt. You have that soap. Where's that drop of oil going to go? Like dissolves like. Where's it going to go? Into the hydrophobic part. Now that's floating around in water. So what happens when the washing machine empties? It goes away with the water. That's how cleaning works. That's how soaps work. They dissolve the hydrophobic part, which is in here in the center, dissolves the oils. The hydrophobic like dissolves like, and away goes the oil that was on your shirt. It goes in the little ball of lipids. Huh? Like a what? Yeah, like dust and a duster, similar. They get attracted to each other because they're both hydrophobic, and as the soap ball, the little ball of hydrophobic molecules form that little sphere, that ball of hydrophobic material with a hydrophilic outside is dissolved in water and gets washed down the drain. Huh? That's how detergent works. All right? That's how, in fact, soap used to be made from animal fat. Soap, before we made it synthetically, soap was made from rendering animal fat and adding lye to it. Adding lye to animal fat and churning it made a soap. And people would use that to wash themselves. Lye is sodium hydroxide. So, no, I'm just giving you an example, a little history of how we as humans have used these things for a very long time. Soap has been around for a very long time, and it was made by using fat, animal fat, which is what? Phospholipids, right? Phospholipids mixed with some sodium hydroxide, which makes a soap, a very strong detergent, and they used to use that lye soap to wash themselves. All right. The last thing, which is just a prelude to what's going to happen next week, because next week we're going to start talking about a cell. I didn't say my cell, right? I said a what? A cell. It turns out that if you had these phospholipids one next to each other, like this, and in fact, let me take that back. Let's go ahead and draw this. And you took those lipids, and remember they have these tails, and you had 2 layers. all right? You have these tails, and you have two layers.
Oh, I know what that is. Them like stick figures.
Then you have, these are phospholipids, right?
Yes.
All right, so this is what's called, these are called a phospholipid bilayer. Phospholipid bilayer. And that is a cell membrane. That's what in general, there's other things to it. We're going to build one next week, but you need to know that this is when you look at a cell, and we draw this cell, and we draw a nucleus, and we draw a membrane inside, and we draw these organelles that have membranes. Not the ones that don't, but the ones that do. And nucleolus. This cell, when you're looking at that drawing, this is this. It's the phospholipid bilayer. There's two layers of phospholipids. And why is that important? Because that allows this cell to be surrounded by what? By water. That's why it allows your body, inside there's water, outside there's water. How can that happen if you have fats everywhere? Because you have that phospholipid bilayer. The phospholipid has two ends, the water-loving side and the water-hating side. Two sides, two ends. So next week we'll be talking about building these membranes, but you need to understand what a phospholipid is. To that end, on Friday you have an exam. That stop at this point, this is all that's going to be on the exam. Not the bilayer, but everything before this bilayer. So make sure you know what's going on.